Okay, I think it is time. So we'll start the AIP Open Seminar for this week. And so it is the mathematical science team that will present. So I've been asked by the office to read you some important notice about this seminar. First, reproduction is prohibited. Second, reproducing all or any part of the content is prohibited without the author's permission. And the seminar will be recorded and the video will be available on the Weekend AIP website later. And if you have any questions or comments, please scroll to the bottom of the page and click the Q&A tab. You can put questions or comments in the box. Okay, so I think we're ready to start. So today, this is basically the plan for today. And so 5 speakers will give talks. And I will first give the overview of the mathematical science team, so what this team is about. So first, a very simple self-introduction. My name is Kenichi Banai. I'm the team leader of the mathematical science team, and I've been affiliated with RECAN starting in 2016. My specialty is arithmetic geometry, which is a field in pure mathematics. And up until very recently, I've been studying various realization of polylogarithms, special values, Hasse-Weil L functions, and block valence and cutoff conjecture, which is pure mathematics and has nothing to do with informatics or machine learning. And so I was very surprised when I was asked to join the AIP as a team leader. And what I had been researching was block valence and cutoff conjecture. But doing this research, this conjecture is a very different conjecture. So the very good method to attack this problem was to do collaborative research with experts of different fields. And so I had experience in collaborating with many mathematicians from many fields. And then when doing machine learning, so machine learning is a very big topic, but many mathematical methods can be used to attack problems in machine learning. So my experience in arithmetic geometry and making collaborative teams, I think, helped to propel our research. And so when I created my team, I called for applicants, postdoctoral applicants to join the team, and very fortunately got many excellent researchers to pure mathematicians to join our team. And because pure mathematics is a very strong method, we're hoping that we can help advance machine learning techniques. The first example that we had success is that of analysis of time series data. So time series is like movement of people or particles, and depending on time, it moves. And then if you have 2 different sets of data, one wants to compare how different they are. That is one mathematical problem. And when in the linear and stable case, when this movement is just multiplication by a matrix, there were various results comparing distance or angles measuring the difference of time series data. But how about the nonlinear or non-stable case was one of the questions that was asked to our team by researchers in AIP. And so in the case of nonlinear or non-stable case, Kawahara, team leader of the AIP, asked us about this, and he had an idea about using reproducing kernel Hilbert space to attack this problem. So what is this reproducing kernel Hilbert space? So if you have some nonlinear dynamical system, so a dynamical system is the data moves with respect to time. But if you take a kernel function and embed this data into a larger Hilbert space, then this becomes a linear operator and then much, much easier to handle. And using such mathematical techniques, so Isao Ishikawa-san, who was a former member of the mathematical science team, we succeeded in defining the distance between 2 time series data using this kernel. And then that was a very good result, generalizing all the other distances that were constructed before. So this was a very good result that we were able to obtain. So Ishikawa-san obtained the Obu Prize from RECAN for his work. And so 3 mathematicians from our team, former, also joined this. And so this was the first results that we got in 2018, but this did not end here. So with Kawahara-san, so Kawahara-san got this big CREST grant about expanding his project concerning these time series data. And many mathematicians from our team joined this CREST. And there is much deeper relation between higher mathematics, like C-star algebra and boundedness of operators. So Ikeda-san, who is the member of our team, will talk a little bit about this project and boundedness of operators when he gives the talk. Yeah, that was our first foray into machine learning, but we have now many other collaborations with other teams within AIP. And many of the results are in the background, so maybe it's not so easy to see. But many of the big results that we have obtained at the AIP, many mathematicians are taking part. So mathematics is playing a very important role in results about artificial intelligence and machine learning. And because we are a group of mathematicians learning about these things, we are also holding math joint seminars, increasingly getting larger every year, about making a community of pure mathematician and theoretical physicists who are interested in machine learning to expand our research. And so today's talk, 4 people from my team will give talks. And so not much about collaborations, but more into the mathematical aspects of what we're doing. So Tojo-san, who started out doing representation theory in pure mathematics, he'll talk about his method to construct exponential families by representation theory. And Kawahara-san, so his background is in physics, but he's been working on very important work concerning very basic theoretical aspects of quantum computing and maybe in the future quantum machine learning. And he just recently received the Obu Prize for his work. So I think this is a very exciting new development in this field. And maybe after a short break, Ikeda-san will talk about operator theoretic approach for time series data generated by nonlinear dynamical system. So this is about the work, continuation of the work started with Kawahara-san's team, and maybe perhaps a mathematical aspect of this. And lastly, Sannai-san, who started out as an expert in algebraic geometry, he'll talk about deep learning with symmetry, how symmetry can simplify some of the constructions in machine learning. So that is our plan for today. Okay, so yeah, that is about what I wanted to talk about today. So during the talks, maybe it is not so easy to answer questions and answers. So maybe after each talk, we have some 5-minute space. So during that time, the speakers will answer questions. And then, yeah. So please feel free to ask questions. And if there are too many questions, then maybe we may not be able to answer, then we'll get back to you if possible, something like that. So that is the plan for today. Yeah. So I hope you enjoy our seminar today, and thank you very much. So Tojo-san, I think you should start at 3:10, so maybe in 2 minutes you can start.
Thank you for the introduction. The title of this talk is a method to construct exponential families by representation theory. This is a joint work with Taro Yoshino. First, I introduce myself shortly. I'm a postdoctoral researcher in mathematical science team. My name is Koichi Tojo. My research field is Lie group theory and representation theory, which study symmetry of spaces. These are my hobbies. Recently, I have enjoyed Japanese chess online. First, we explain our aim of this research and demonstrate family of distributions on the upper half plane with Poincare metric, so that we can share our aim of this research. One of our aim is to suggest good families of probability distributions on important spaces. To attain our goal, we propose a method to construct a family of distributions by using representation theory. Here, we demonstrate a family of distributions on the upper half plane with Poincare metric obtained by our method. The right side is the upper half plane with Poincare metric. This is a family of distributions on the upper half plane with three-dimensional parameter space. Our aim is to suggest good families of distributions on important spaces, such as the upper half plane, spheres, and the hyperbolic space, or more generally, symmetric spaces. This is a plan of this talk. First, we will talk about background and our motivation. Next, we will explain our method. We call it the Modage method here. In the field of machine learning, learning using a family of probability measures is one of important methods. Here, learning is mathematically to optimize the parameters in the family of probability measures. We often use exponential families as a probability model. This is a good class of families of probability measures. In fact, exponential families are important subject in the field of information geometry and are useful for Bayesian inference and include many widely used families such as normal distributions. These are examples of exponential families. Exponential families include normal distributions, Bernoulli distributions, gamma distributions, Wishart distributions, von Mises distributions, and so on. Categorical distribution is a generalization of Bernoulli distribution, and Wishart distribution can be regarded as a generalization of gamma distribution. Von Mises distribution is well studied in the field of directional statistics. Here is our definition of exponential family. We modified well-known definition in the field of statistics for convenience to representation theory. Roughly speaking, exponential families is a family of distributions having this exponential form. More precisely, let X be a manifold, and Rx the set of all random measures. The set of all random measures. Subset P of Rx is an exponential family on X if there exists a triple mu VT satisfying the following four conditions. Mu is a random measure, and V is a finite dimensional vector space over R. T is a continuous map, and for any element P in P, there exists a element P theta of the duals of the vector space V, satisfying this equality. Here, phi theta is a log normalizer. We call the triple mu VT a realization of P. Some texts call this triple representation, but to avoid conflict with group representation, we call realization in this talk. Let us see a typical example, a family of normal distributions. The family of normal distribution it has this form with parameter sigma and m. M is the mean, and the square of sigma is the variance of this distribution. This is an exponential family in our sense. In fact, we can take a realization mu bt like this. This is not unique, but easiest realization with regard to the dimension of V. By definition, there are too many exponential families. However, only a small part of them are widely used, like this picture. Oops, sorry, it is too small to see. Let us enlarge here. There are good exponential families we often use. From this picture, we can expect there exist good exponential families. So we want a framework to understand these good families systematically. This is our motivation. The following observation gives us a hint to attain our purpose. That is, useful families, useful exponential families have the same symmetry as the sample space. Mathematically, the sample space is a homogeneous space G mod H, and the family on the sample space is invariant under the induced G action. Here, G is a Lie group, and H is a closed subgroup of G. Writing a space by the form G mod H is mathematically a description for focusing on symmetry. So our idea is to use representation theory, which is a theory of symmetry. We proposed a method to construct exponential families by using representation theory. In this talk, we call it G mod H method. G mod H method has following two good properties. G mod H method can generalize many well-known families. Moreover, families obtained by G mod H method can be classified by using representation theory. So we can expect that new families obtained by this method are good. Now we will explain G mod H method. First, let us see a method roughly. Later, we will explain method step by step. G mod H method is a method to construct a family of probability measures on a homogeneous space G mod H from the following two inputs. One is a finite dimensional real representation of G, and the other is a non-zero H fixed vector with regard to this representation. Here, GLV is the group consisting of all linear isomorphisms of V. We will see the details of G mod H method step by step later, but roughly speaking, we take the following 5 steps. In step 1, we take Lie group G and the closed subgroup H of G and consider homogeneous space G mod H denoted by X. In step 2, X is our sample space. In step 2, we take 2 inputs, finite dimensional real representation rho V and H fixed vector. In step 3, we consider the set omega GH of all non-zero relatively G-invariant measures on X, which is defined later. In step 4, we make measures parameterized by direct product of the dual of V and omega GH. And in step 5, in the final step 5, we normalize them. Before moving to each step, let us see examples obtained by the Modage method. Our method generates useful families of distributions systematically. In fact, by choosing these inputs, G, H, V, V0, we obtain these useful family of distributions. Choosing inputs GH, V, V0 is to give an interpretation of symmetry of the family of distributions. We mark that these are not all of examples obtained by our method. To explain each step of the Modage method, we would like to apply the Modage method to construct normal distributions in the top of this table. Now we enter the details of the Modage method. In the left side, we explain each step in representation theory. And in the right side, we demonstrate how the family of normal distributions is generated by the Modage method. In step 1, we prepare a sample space with symmetry. In the representation theory side, we take a Lie group G, which describes the symmetry, a closed subgroup H of G, and the homogeneous space G mod H, noted by X here. In the normal distribution side, R has a symmetry of scaling and translation. So we take the corresponding semi-direct product, semi-direct group G, and its closed subgroup H like this. Here, the first component represents scaling, and the second component represents translation. Then we can identify a G mod H with a real line via this map. We reconstruct the family of normal distributions on R with the well-known form. In step 2, in the representation theory side, we give inputs to generate distributions. We take a finite dimensional real vector space, representation law of Z, and non-zero H fixed vector V0. Here GLV is the set of all linear isomorphisms of V. In the normal distribution side, we take the 3 inputs like this, respectively. Here, Sim2R is the vector space of all symmetric matrices of size 2. We can easily check that V0 is H fixed. By considering the case, we can easily check that V0 is H fixed by considering the case X is equal to 0. In step 3, we consider measures compatible with symmetry. In the normal distribution side, a measure compatible with scaling and translation is essentially the Lebesgue measure. Mathematically, measures compatible with symmetry means relatively Lie invariant measures. The definition of relatively Lie invariant measure is given in definition 2.3. So we consider the set of all non-zero relatively Lie invariant measures with X up to positive scalar. We denote it by omega GH. This depends only on the pair G and H. We regard an element of omega GH as a parameter later. In step 4, we construct measures on X with symmetry. More precisely, in the representation theory side, we define measures parameterized by the direct product of the dual of V, the vector space V, and omega GH by as follows. Here, rho is abbreviated, and this is well defined because V0 is H fixed. In the normal distribution side, by taking natural inner product on V, we obtain measures parameterized by real numbers θ1, θ2, and θ3. In the final step 5, we normalize the measures above. We denote by large theta the set of parameters such that the measure is integrable on X. We call it parameter space in this talk. Then by normalizing the measures, we obtain the set of probability measures P theta parameterized by parameter space. Here, phi theta is the log normalizer. In the normal distribution side, we can compute the parameter space, the log normalizer, and P theta like this. Namely, we obtain the family of probability measures on R as shown. Moreover, by changing variables here, we obtain the well-known form of normal distributions. Now we will see the properties of G-Modage method. The family obtained in this way has good properties. Namely, the family obtained by this method is the invariant exponential family on G-Modage. For example, in the normal distributions case, the action means scaling and translation. So this proposition corresponds to the fact that the distribution transformed by scaling or translation from normal distribution is also a normal distribution. Then the following question 2.5 naturally arises. Are any G-invariant exponential families on G-Modage obtained by our method? The answer is yes, under my assumption. So if we accept the answer, roughly speaking, there exists a correspondence between the set of G-invariant exponential family on G-Modage and the set of families on G-Modage obtained by G-Modage method. Let us see the answer to question 2.5 more precisely. Let P be a G-invariant exponential family on G-Modage, and we assume that G-Modage admit the non-zero-relativity G-invariant measure, and theta is open. Then P is a subfamily of a certain family obtained by G-Modage method. For the detail, please see our paper. Finally, we leave a take-home message. One of our aims is to suggest new useful families of distributions for applications by using G-Modage method. So if you want a good family of distributions on some spaces, please tell us the spaces. We will try to propose good families of distributions on them. These are references of this talk. Thank you very much for your listening.
Tojo-san, thank you very much for your talk.
Thank you very much.
Yeah. So there were some questions on the Q&A. Have you seen them?
Yes.
So the first question by Shibin is, can you explain more about what does good exponential families stand for?
In my talk, good means this property. That is, the family obtained, the family is good means, in a sense, is G-invariant in this sense.
Okay. So Shibin, does this answer your question, do you think? Or...
Sorry. And next question.
Okay, I think that's
right.
okay. Okay, and the other question is what is Lie? And I think you answered during your talk.
Yes. Yes.
So you meant as Lie group, or
yes.
so group with a structure of a manifold, and all the structures are compatible.
Yes.
Okay. Okay. Yeah. So any other questions or comments? Okay. Can you see the next question?
Yes.
So the question is, please, can you explain the role of V in this? What happens if you choose different modules? Example, for the categorical distribution, you use the symmetric group and its natural subgroup, but took the trivial module. Does using a different module give anything interesting?
In general, if we consider high-dimensional if we choose high-dimensional representation, then we obtain a family with big parameter spaces. So categorical distribution, to generate categorical distribution, we use symmetric group and natural representation. It is a simple family of distribution obtained by our method. If we use more complicated representation, then we obtain more complicated family of distributions on the set of numbers 1 to n. So if we choose another, if we choose another representation, then we can get a new family of distributions. It is interesting thing, and our next future work is to classify G-invariant exponential families on homogeneous spaces. Then we are very interested in the question. Thank you very much for your question.
Okay. Does this answer your question? Okay, thank you very much. Are there any other questions or comments? No. If not, so Tojo-san, thank you very much for your talk.
Thank you very much for your listening.
And yeah, if you have further questions, then please ask on Q&A because we can see them also later.
Okay, let's start my presentation. Hello, my name is Tomotaka Kuwahara. I am now a research scientist in AIP mathematical science team. I got the PhD in University of Tokyo and then moved to AIMR in Tohoku University. And after 2017, I joined the AIP. Today, I will talk about my research in these 3 years, which I title the information theoretic structure of the quantum Boltzmann distribution. Yeah, I know that most of you are not familiar to quantum mechanics, so I prepared the slide so that one can understand the content without the knowledge of quantum mechanics. Instead, I don't mention any details of the results. I am sorry on the point. Okay, I start from my main research target, namely the quantum computer. To explain the advantage of the quantum computer, I first briefly explain the key difference between the classical world and the quantum world. Let's consider coin toss. If you have a coin of 500 yen and try the coin toss, then after the coin drop to the ground, you can confirm the heads or tails. At least if you are living the same world as mine. But in quantum world, this common sense breaks down. The coin can take the state of the heads and tails simultaneously. This is known as the superposition principles. By using this nature of the quantum mechanics, one scientist came up with an idea in 1980s to develop a much faster computer than standard computer, which we usually utilize. The name of this scientist is Richard Feynman in the United States. The usefulness of the quantum computer has been first demonstrated theoretically by Peter Shor, maybe in 2094, who established a quantum algorithm to solve the factorization problem. The factorization problem is believed to be very hard to solve by standard computer, and this factorization problem is used to the most of the cryptographies. Then we have a question: is it possible to realize the quantum computers? On this point, until very recently, the quantum computation has been only a theoretical playground, and no one couldn't ensure the realistic impact on the world. But the situation is changing. The most famous breakthrough was given by Google. Google developed a small quantum computer, which is called Sycamore, with 53 quantum qubits. Qubit is an abbreviation of quantum bit, and the number of qubits is the important measure for the size of quantum computer. In the Google's experiment, they performed a task of so-called random circuit sampling by using the quantum computer. This is known to be very difficult by using the classical computer. In the experiment, their task needs 10,000 years if we utilize only the classical computer, but they achieved only 200 seconds by using the quantum computer. That is, they achieved, this is 1.5 billion times faster than the classical computer. In fact, this estimation of 10,000 years is controversy, but anyway, this is great leap on the quantum computation. I guess that you may ask, is it useful to solve the random circuit sampling much faster? For this question, my answer is no. I don't know any useful practical application by using the random circuit sampling as a subroutines. Now, various researchers aim to develop more useful algorithm by using the quantum computer. For this question, the quantum many-body physics gives one answer. I will explain what is the quantum many-body physics. This is a picture of two-dimensional quantum many-body systems. Each of the dots is a quantum particle. The quantum particles interact with each other, where the interaction exists only for nearest neighbor particles. Even if we know one particle properties, the cooperation of many particles often is unexpected phenomena. For example, superconducting, quantum speed liquid, topological insulator, superfluid, which is seen in helium-4, and so on. The quantum many-body physics aim to compute the properties of the quantum many-body systems. To answer the question, there is a research field which is named Hamiltonian Complexity. In the Hamiltonian Complexity, as the name tells, we aim to clarify the complexity of quantum Hamiltonian. The Hamiltonian is an energy function of quantum particles, and the Hamiltonian includes all the information on the quantum many-body systems. Mathematically, if we know the Hamiltonian, we can construct the Schrödinger equation. Schrödinger equation is this equation, this derivative equation. By solving the Schrödinger equation, we can understand all the properties in principle. By the way, how difficult is it to compute the properties of many-body Hamiltonians? One of the most fundamental tasks is, for example, to find the lowest energy states in quantum many-body Hamiltonians. To this question, the answer is very pessimistic. As shown by Alexei Kitaev, the complexity class is included in QMA complete class. Very roughly speaking, this problem is very hard even for quantum computers. But this fact means that the most difficult problem in the quantum many-body physics is hard to simulate by quantum computer. That is, not all the problem is hard to solve. In fact, many of the practical problems in quantum many-body physics can be efficiently solved. Then we have a very fundamental question. In what cases can we efficiently simulate the quantum Hamiltonians? Here, the simulation means the computation of the properties of quantum Hamiltonian. This is the main research target of the Hamiltonian complexity, as well as my research topic. By the way, some of you may wonder why Hamiltonian is important. Hamiltonian is physical concept. You may think I am now attending the seminar in RIKEN Advanced Intelligence Project. So yes, is it related to practically important problems, including machine learning? To answer the question, my answer is yes. The machine learning and the quantum many-body physics is connected in very deep ways. I want to notice that the earliest neural network, the Boltzmann machine, is based on the statistical physics. I first mentioned that almost all the practically important problems in quantum computation is included in the QMA class. The QMA class is very rough speaking. This is the quantum version of the NP class. That is, the class of the problem as when an answer for the problem is given, then we can easily verify the correctness of the answer by using the quantum computer. This is a very important class and a very ubiquitous class of the the problem in quantum computations. Anyway, the point is that any problem, in other words, if we can solve the quantum many-body problems, we can solve all the problems in QMA class. So if we can develop efficient algorithms for solving many-body problems, we can also apply these algorithms to practical problems, including machine learning. As a concrete example, I would like to show the semi-definite programming problem, which is deeply related to the quantum Gibbs sampling, which is one of the most fundamental problems in the quantum many-body problem. Okay, so I here show my achievement during my studies in RIKEN, AIP. I mainly investigate the Hamiltonian complexity. Now the Hamiltonian complexity is a fundamental research target in quantum information theory. In international conference, the Hamiltonian complexity constitutes a big block session. The Hamiltonian complexity is highly mathematical research field, and various important open problems are well defined. My aim is to solve these mathematical open problems. I like to solve well-defined open problems since it clearly identifies who is the best in the research fields. Anyway, I have succeeded several very important open problems which is related to area law conjectures, quantum Markov conjecture, linear light cone problem, eigenstate summarization hypothesis, and so on. All these achievements are published in the top journals such as PRL, Physical Review Letters, Physical Review X, Nature Communications, and Nature Physics. Also, they are chosen to 5 talks in top conference on the quantum computing. Now, only a few, usually 1 or 2 Japanese researchers are chosen to the talks in such a top conference on the quantum information. So I hope that more Japanese researchers will have influences in the field. In the following, I want to show a quantum Boltzmann distribution as a specific example for these achievements. I first show what is the quantum Boltzmann distribution. The quantum Boltzmann distribution is a typical quantum state after a long time evolution. When a quantum state is put on a room with a temperature T, then after long time evolution by the Schrödinger equation, the quantum state reduces to the quantum Boltzmann distribution. The quantum Boltzmann distribution is mathematically described by this form, but I don't know, I don't explain the details. This V is a partition function, and this exponential minus beta, T over H over T. Yeah, now H is given by some matrix, and rho is also given by the matrix, and the quantum state is given by the formal density matrix. Anyway, the point is that the quantum Boltzmann distribution is only determined, by the temperature and the Hamiltonian. I remind us that the Hamiltonian is the energy function of the quantum many-body particles. I want to show several applications of quantum Boltzmann distributions. The first application is semi-definite programming, which I denote SDP. This is very important application. The setup of the semi-definite programming is mathematically formulated by this form, but I don't mention on the details. This is the generalization of the linear programming problem. Very roughly speaking, the semi-definite programming aims to maximize the target function and the malicious constraint. The semi-definite programming is one of the most important class of the many-body optimization problems, and it is deeply related to the kernel-based machine learning, such as the support vector machines. Please see, for example, these review articles. Usually, as the number of constraints increases, the computation of the solution of SDP needs a large computational time, by using the classical computer. But as has been shown by Brandau and Svoboda, there exists a quantum algorithm which achieves exponential speed up compared with classical computers. The only condition for this exponential speed up is that the quantum Gibbs sampling is efficiently performed by the quantum computer. The quantum Gibbs sampling is the preparation of the quantum Boltzmann distribution by the quantum computers. As far as I know, the application to SDP is one of the most important candidates to demonstrate the power of quantum computer. The second application is the Hamiltonian learning. The problem is roughly given by this statement. Can we learn the quantum Hamiltonian only from the quantum Boltzmann distribution? Here, the Hamiltonian is energy function of the system. I explain why it is very important in the context of machine learning. The first point, this is not related to the machine learning, but this is very fundamental point in quantum mechanics. As the first point, the world we live is governed by the Schrödinger equation. The Schrödinger equation is the most fundamental equation in the quantum mechanics. And by solving this Schrödinger equation, we can in principle clarify all the phenomena in the nature. On the other hand, in order to obtain the Schrödinger equation, it is necessary to know the explicit form of the Hamiltonian. And the form of the Hamiltonian depends on the system details. By the recent experimental development, the measure in the level of the quantum particle is now possible, and we can directly estimate the Hamiltonian. There already exists some experimental realization of Hamiltonian learning, maybe by using the cold atom setup. The second point is the quantum Boltzmann machine learning. The quantum Boltzmann machine learning is one of the quantum neural network which is utilized for the quantum machine learning. In the learning of the quantum Boltzmann machine, we necessarily need to perform the Hamiltonian learning from the quantum Boltzmann distribution. Okay, so I will show the Hamiltonian learning in more detail. As the first point, the quantum Boltzmann distribution includes the full information of the Hamiltonian. As shown by this equation, the quantum Boltzmann distribution is only characterized by the temperature and the Hamiltonian. Then, thanks to the recent quantum technologies, we can perform a measurement of each of the quantum particles, and we obtain classical data samples. Then by using this classical data sample, we estimate the quantum Hamiltonian. In the Hamiltonian learning, the most essential problem is the sample complexity. In principle, we cannot learn the Hamiltonian only by one sample. From one sample of the quantum Boltzmann distribution, we can obtain one data sample, but this is insufficient. We need many copies of the same quantum Boltzmann distribution. The sample complexity for the Hamiltonian learning asks how many samples are required to run the Hamiltonian with desired precision error. This problem is not restricted to the quantum Hamiltonians. When we consider the classical Hamiltonian learning, which is corresponding to the Boltzmann machine learning, the sample complexity is well understood. The difficulty is that almost all the techniques in the classical setup, the classical Hamiltonian learning, no longer apply to quantum cases. As one of our biggest triumphs, we can solve the sample complexity problem for generic Hamiltonian learning. We identify the number of samples required for the Hamiltonian learning is given by n to the power of alpha. Here, alpha is given from 1/2 to 3. And the n is the number of quantum particles in quantum Boltzmann distributions. In this way, we proved that the polynomial number of samples are necessary and sufficient. These results are accepted in Nature Physics and also presented in Fox 2020 and QIP 2021. In the derivation, we utilize various techniques from quantum many-body physics, to name a few: the Lieb-Robinson bound, quantum belief propagation, and connection between global and local energy distribution, and so on. Okay, I summarize the talk and show future problem. My research motivation lies in the research field of Hamiltonian complexity. These have a deep connection with the practical application, including the machine learning. As I shown example of the semi-definite programming. In my study, I have solved several important mathematical open problems. As one example, I have shown the resolution of the sample complexity in the quantum Hamiltonian learning. As future work, I would like to challenge great open problems in the field of quantum many-body physics, such as the Eliaro conjecture, quantum Markov conjecture, and quantum PCP conjecture, and so on. That's all of my presentation. Thank you for listening.
Kohara-san, thank you very much for your talk. So So are there any questions or comments for Kuwahara-san? Yeah. Yes, I have a question. So yeah, can you go back to one page back? So what is the quantum Markov conjecture?
Oh, the quantum Markov conjecture is a condition. I mean, in classical words, the quantum Markov property is characterized by the conditional independence. I mean, the between two subsystems. I mean, let us consider tripartite systems A and B and C. Then the Markov property implies that if A and C is satisfied, I mean, the A and C is, I mean, conditionally independent for the subsystem B. And if for any tripartite systems, two subsystems conditionally independent for the other subsystems, then the classical probability distribution is set to satisfy the Markov properties. Then the Markov property is characterized by the very famous Hammersley-Clifford theorems. The Hammersley-Clifford theorem implies that the quantum Markov network, I mean the quantum Markov probability distribution is equivalent to the quantum Boltzmann distribution, the classical Boltzmann distributions. Then the classical Boltzmann distribution is known to be equivalent to the Markov network. And the quantum Markov conjecture is whether it is also true for the equivalence of the quantum Markov network and the quantum Boltzmann distribution.
I see.
This is the conjecture, and this is deeply related. Oh, this is very deeply related to various kinds of, I mean, the open problems in quantum information theory. For example, the quantum PCP conjecture is also related to the quantum Markov conjecture, but it is difficult to explain why this is important.
Okay, I see. Oh, thank you very much. So I think you have a question on your Q&A from Shibing. So the question is, what is the essential difference between quantum Boltzmann machine and Boltzmann machine in machine learning field? Are they equivalent?
In fact, the quantum Boltzmann machine learning is now very heuristic. So there are only several examples which has shown that quantum Boltzmann machine learning is more efficient than classical machine learning. But the condition is very and if we consider and if we restrict ourselves to some very specific case, the quantum Boltzmann machine learning is shown to be more powerful than the classical machine learning. But I don't know whether or not the quantum Boltzmann machine learning is truly more powerful than the classical Boltzmann machines.
I'm sorry. I think the question was: is there a difference between quantum Boltzmann machine and Boltzmann machine and machine learning? So that means
The machine the quantum Boltzmann machine learning is one method to solve the machine learning problem. In this sense, the quantum Boltzmann machine learning is also included in the machine learning.
But so they're equivalent, or essentially the same.
In this, only the method, quantum Boltzmann machine learning is one of the methods of the machine learning.
Okay. Does that answer your question? I guess. Okay. And another question is by Sheriff Hashima. So, what are useful applications in wireless communications? Do you have any?
Wireless? Oh,
Wireless communications. Is there any relation to what you're doing to such applications?
wireless.
Mhm. Mhm. Mhm.
Sorry. What means the wireless communications? That if you
Mhm.
mean for example, I mean
Mhm.
like internet systems, then
Mhm. Mhm.
quantum information is very important in the sense of the cryptography, because as I have shown that Shor's algorithm can solve the factorization problem. So if the factorization problem can be solved by the quantum computers, then all the classical cryptography is very fragile to the quantum computer. So now, it is proposed that the quantum cryptography is more, much more, the powerful to the, powerful to the,
Preventing decoding.
Yes,
Yeah.
in this sense. So so by using the quantum mechanics, some kinds of quantum cryptography is now developing, and several prototype has been already realized by, for example, Chinese Academy of Science or NTT.
Okay. I hope that answers the question. So, are there any questions or comments for Kohara-san? Okay. Then think not. Then thank you very much for your talk. どうもありがとうございました. Okay.
Thank you.
Okay. Yeah, so maybe we take a break for 10 minutes. So I meant to mention this, but I did not. So if you're a mathematician or maybe a theoretical physicist interested in working with our team, right now RIKEN is advertising position SPDR, special postdoctoral researcher positions for the year starting 2022. And so if you're interested, the registration for application is until April 8th, and the final application is until April 15th. So visit the homepage and apply to our team or any other teams in RIKEN AIP. And also there is another center called Items in RIKEN, which also mathematicians and physicists can apply to. So this is for postdoctoral researchers who will have a PhD by 2022. If you are a doctoral student or someone who is going to go to the doctoral program, then there's another program called the JRA, Junior Research Associate, also for RIKEN, for PhD students. And the deadline for next April is usually around November. So if you're interested in applying, then around this time, please contact us or look at the RIKEN homepage and apply. So yeah. And so yeah, this is that. And one more thing. So I should advertise the AIP Open Seminar series. So every week, one team at AIP will present what their team is doing. So this week it's for the mathematical science team. So the schedule for the next weeks are as follows. I think many interesting talks, so please attend if you're interested. So that is the announcement for now. And so we will resume by Ikeda-san's talk at 4:10. So yeah, short break until then. Thank you very much. Okay, I think it's time. So the next speaker is Ikeda-san from our team, and yeah, he'll talk about operator theoretic approach for time series data generated by nonlinear dynamical systems. So please.
Thank you very much. So my name is Masahiro Ikeda. Title is Operator Theoretic Approach for Time Series Data Generated by Nonlinear Dynamical System. So before going to main topic, so I will briefly introduce myself. So yeah, I got a PhD in 2013, and the topic was pure mathematics, especially the nonlinear PDE. And I experienced several postdocs at several universities. And after, since 2017, I came to Riken Center for AIP, and now I am research scientist Riken Center for AIP. And my majors are differential equations and function spaces and Fourier analysis. And since I came to Riken AIP, I started to study dynamical systems, spectral graph theory, and machine learning closely related to data analysis. And today's main topic, function spaces and Fourier analysis. And yeah, let's go to the main topic. And so the Koopman operator is one of the keywords. Some people, okay. And Koopman operator is a keyword of this talk. So I will introduce the definition precisely. So M and N are sets, and F is a map from M to N, possibly nonlinear, and which is often called dynamical system. X and M are function spaces, possibly infinite dimensional. And X functions is function spaces on M, and Y is function space on N. And CF is called Koopman operator. CF is an operator from Y to X, is a linear operator with the domain. The domain of CF is defined like this. So H in Y, the composition of H and F is in X. And then the Koopman operator is defined by the composition of H and F. And the relation can be understood the following pictures. So F is a dynamical system, possibly nonlinear. And so time evolution of the dynamics, the analysis of time evolution is not so easy. So by using the Koopman operator, we can linearize the system at the right picture. So, and yes, so but F is nonlinear, but Koopman operator is linear. So functional analysis or linear algebra can be effective to study the property of Koopman operator. So that's why the analysis of Koopman operator is getting popular and popular in application to data analysis and machine learning. And so originally, so the Koopman operator is extensively studied in complex analysis in pure mathematics. In that field, this operator is called composition operator. In theoretical physics, this operator is called Koopman operator. And in signal processing, this operator is called time warping. And next. Okay, so yeah, I will introduce several previous results for application. So the Banna sensei introduced. So in 2018, we introduced metric, more precisely positive definite kernel. I will give a definition precisely later to compare two dynamical systems by using the Perron-Frobenius operator, which is adjoint of the Koopman operator, as I defined before, on RKHS. RKHS is a Hilbert space associated with positive definite kernel, which will be explained later. And moreover, this metric has several advantages compared to the previous studies, but we omit the detail. So this paper is published in New Lips 2018. This is the top conference of machine learning. And I will introduce the second previous result. Actually, so we generalized the previous theorem to random dynamical systems. Random dynamical system is a class of dynamical system taking into account randomness via Perron-Frobenius operator as before on operator valued RKHS. Operator valued RKHS is one of the generalization of RKHS. And moreover, this metric gives a generalization of kernel maximum mean discrepancy for two stochastic processes. And this metric has a relation to Hilbert-Schmidt independence criteria. But the detail, please see the archive paper. And I will introduce the final previous result. This study is for estimate of these operators. We proposed Anomaly and shift Anomaly methods, which is one of the Kirillov subspace methods to estimate the Perron-Frobenius operator on RKHS only with finite data. And moreover, the estimated Perron-Frobenius operator can be applicable to, for example, anomaly detection, and which is advantage compared to the previous study. This paper is also published in JMLR 2020, which is one of the top journal in machine learning. And so, okay, let's go to the, okay, today I'd like to introduce one mathematical result for the Koopman operator, especially boundedness and preserving property. So mathematical properties such as boundedness and spectrum of Koopman operator depend on the choice of function spaces x and y. The choice of x and y, for example, Sobolev space, Bezov space, and some other function spaces, and RKHS. So RKHS is today's main object. And today we focus on boundedness of this operator. So boundedness of the Koopman operator is important to provide theoretical guarantee for application, for example, dynamic mode decomposition. However, proof of boundedness of Koopman operator is not easy in general. So the detailed analysis of by Fourier analysis is needed. And so yeah, the recent result of boundedness of Koopman operator you can see the recent archive paper. And boundedness is equivalent to so-called preserving property. So I will explain one fact. So Koopman operator is a closed operator. And by using closed operator theorem, we can get the following. CF is bounded if and only if. So the domain of CF is equal to Y. So this is so-called preserving property. So this is important in the field of signal processing. So to prove boundedness, so it suffices to prove this preserving property. So okay, I will introduce reproducing kernel Hilbert space precisely. So this space has various applications to statistics and machine learning. Because we may regard each data point as a function in a Hilbert space. So first I will give a definition, positive definite kernel. So a function k m times from m times m to c is a positive definite kernel if for any r and x1 xr in m the gram matrix kxi xj is positive semi-definite Hermitian matrix. And the following Moore-Alonjine theorem is well known, namely that K is a positive definite kernel, then there exists unique Hilbert space. We call RKHS for short, such that the following property hold. For any x in M, called K sub x, K sub x is defined K x dot, Kx is in HK, and the so-called reproducing property holds. H, the inner product H and Kx is equal to H of x. And so next, we introduce a positive definite function. This is a class of functions. And so we say u, we say a function u from D to C is a positive definite function if ux minus y is a positive definite kernel. And this function is widely used in application. And roughly speaking, this function is a Fourier transform of non-negative function. And example of this function is like this. So e to the power minus absolute value of x to the power p. So if p is 1, this generates Laplacian kernel. If p is 2, this is Gaussian. And sine x over x is called zinc function, and this function is oscillate as x tends to infinity. And so for positive definite function, Bohonnan theorem is well known. This is the characterization of positive definite function. So namely, let u is a continuous function from T to C, and u is a positive definite function if there exists a finite polar measure such that ux is equal to the Fourier transform of the polar measure, which is written the right-hand side. And this is a characterization of positive definite function. And so we want to discuss the boundedness of Koopman operator on RKHS, but we need more concrete expression of RKHS. So in fact, Moore-Alonjine theorem only guarantees existence of RKHS. So the following proposition is well known. So W is in L1 function and L infinity function, and W is non-negative, and K is defined like this. So the Fourier transform W of x minus y. Then so K becomes a positive definite kernel. So in this case, HK can be written like this. So f is in L2, and this integral is finite. So actually, W decays the high frequency component of W decays. So actually, F decays fast. Yes, yes. And okay, let me give an example. If W is a characteristic function on minus pi to pi, then HK can be written more concretely like this. So F in L2, and the Fourier transform of F is banished outside the support of F. So this function is often called band limited function. Okay, let me give main result. So the detail can be seen this archive paper. This is joint work, Ishikawa-san and San Sensei. They are a member of mathematical science team. And so our result is related to Clark conjecture. Clark conjecture is a theoretical conjecture in signal processing. Roughly speaking, only a fine time mapping preserves bound to limitedness. And more precisely, Clark conjecture is as follows. So let F be signal, namely F is in L2 on R. S be time mapping, namely S is a function on R, and S is continuous. And Clark conjecture is if F is band limited and the composition of F and S is also band limited, then S is affine, namely S is can be expressed as AX plus B for some A and B. And so we can rephrase mathematical formulation. So let K is Fourier transform of characteristic function on minus pi to pi. This can be expressed as zinc function. And Clark conjecture is equivalent to the following. If the composition of if the domain of Koopman operator is equal to RKHS, then S is affine. And so namely, if the Koopman operator on RKHS is bounded, then the original map S is affine. So, so Clark conjecture has already been solved by several authors. So Chacon Gimenez in 2007, and Ko-chan and Clark himself, and others. And they, they apply Fourier's theorem, namely, if F and G are entire, and the composition of F and Z is of finite order, then F is of order 0 unless G is polynomial. So they essentially depend. The proof is essentially depends on finiteness of order. So this is verified if W is compact support. You can use Fourier's theorem. So natural question arises. So what happens if W is not compactly supported, like Gaussian? Okay. Okay. I will introduce our main result, but there there are many there are some notation needed. So W is non-zero and W is in L1 and L infinity, and W is non-negative as before. And we assume W satisfies minus log W over absolute value of C tends to infinity as absolute value of C tends to infinity. So this assumption means W decays faster than any exponential function. And by using W, so L to W is the weighted Lebesgue space, and the weight is W. And by using the assumption of W, L to W contains the space of polynomials Pn. This polynomial, the degree of total degree of polynomial is less than n. And K is defined the Fourier transform W of x minus y. And so in this case, the Fourier transform W is positive definite function, and K is positive definite kernel. And we introduce multiplication operator. So namely for Z in CD, MZ is a multiplication operator on L to W. So MZ means a multiplication e to the power minus I Z transpose of Z dot C times C. And so we know that. So this operator is unbounded unless W is compact support. So if we want to treat the function W whose compact is not support, we have to take care this boundedness. And also we introduce the subset of matrix. So we denote GW. W is defined like this. So W of a transpose C is greater than lambda times WC for some lambda. And we know that if W is spherical, then the space of orthogonal matrices is included KW. By preparing this notation and assumption, the main result is as follows. So we assume the two conditions, there exists B such that for any Y, these two quantities are bounded. And GW, the span of GW is equal to the whole matrices. Then for any U is subset on RT, and for any U, then the domain of CF is equal to HK. Then F is affine. So this is the main result. So namely, finally, so this theorem says for application to nonlinear analysis by Kubma operator, we have to carefully choose function spaces. So yeah, especially Gaussian kernel is included this theorem. Okay, sorry. Okay, thank you very much.
Okay, yeah, thank you very much for your talk. So, okay. So are there any questions or comments on Ikeda-san's talk? No? Yeah, it's okay. Okay. So when you say you have to carefully choose function spaces, so So what is the good space in your case? Yeah.
Sorry.
Mhm.
Sorry, could you repeat?
Yeah.
Again?
Yeah. So what functional spaces was good for you? Yeah.
Good. So this.
Yeah.
So Gaussian. So actually, we want to treat nonlinear
right.
map. But if you choose Gaussian Gaussian kernel, but you cannot use the nonlinear function. And but Laplacian Laplacian kernel is not Laplacian kernel does not satisfy this assumption. So you might be treat the nonlinear map of F, nonlinear map of F.
Okay. Yeah. Okay. Thank you very much. Any other questions or comments? Okay. If not, thank you very much. Okay. So our last speaker for today is Sannai-san. So.
Yes. Thank you. So, hello, I'm Akiyoshi Sannai. So I'm a research scientist at mathematical science team. Today I'm talking about deep learning with symmetry. So let me start with self-introduction. So the name is Akiyoshi Sannai. And I'm interested in deep learning and symmetric neural nets, graph theory, and optimization problem. So, so before coming to weekend, I studied algebraic geometry and singularity theory. So I got my PhD at University of Tokyo. And from 2017, I joined weekend and started to study machine learning. So this is a picture today. So we start with mathematical classification of tasks. So not tasks, but property, mathematical property. We start with mathematical property. So today is symmetry. So the objective is, so we study on your net for symmetric tasks. I will give you examples later based on group theory. And there are two kinds of symmetries we deal with. So one is equivalence and another is invariance. And under the prior knowledge of symmetry, specific neural networks were with small samples. That this is done in deep sets paper. And basically, we consider the group of permutations and its subgroup today. So the first example of task is equivalent tasks. So this is set anomaly detection. So in each line, there is an anomaly. So others have two common properties. So each line of picture is the input. So this task has the following property. So the input is 16 pictures, and if B is an anomaly, then of course the answer is 2. Number 2 is an anomaly. So, and if you swap 2 and 3, then the answer is 3. But this is also swapping in the answer. So this is equivalent property. This is one symmetry. And another one is invariance. So this is it. For example, if you classify the point cloud data, then so other data we need to all the points, but even if we permutate the order of points, the result is same. Okay, so let me quickly review the group theory. So if you are not familiar with group theory, so you can regard group as a set of regular matrices that contains the unit matrix and closed by a product and taking inverse matrix. The formal definition is below. So the first one is, for example, in the case of matrices, this is associative rule. So the result does not depend on the order of taking multiplication. The second one is so existence of the unit matrix, and the unit matrix multiplying unit matrix is nothing, so stable A. And the third one is there is a inverse matrix in the set. So this is an example again. So let SM be the set of permutations on 1 to m. M is the number of point clouds, number of points in point clouds. So permutation can be written as a matrix, regular matrix, and we can take inverse. And another one is SO3, which is a rotation group in three-dimensional vector space, and also the set of regular matrices of size n by n. Oh, sorry. Instead, we focus on the following functions. So let G be a subgroup of permutations. The first one is invariant, G invariance. So function is said to be G invariant if, so if you multiply the matrix to input, the output is same as the value without multiplication. The second one is G equivalent. So the function is said to be G equivalent if you multiply G input, then the output is same as the output of original X multiplied by G. This is G equivalent. Okay. So then we go to permutation equivalent neural nets. So the first one is permutation equivalence layer. So there is a lemma in deep sets, a function or transformation by one layer, which is multiplication by a matrix, and activation, sigma is activation function. So this is permutation equivalent if and only if theta is the following form. So lambda I plus gamma all one matrix. So the point is that, so if we don't know about equivalence, then the matrix has m square parameters. But if we know the equivalence, then we can compress the number of parameters to 2. So this is a big difference. So this is one layer. So by stacking this layer, we get a deep neural net. So permutation equivariant deep neural net. So each transformation, since each transformation is permutation equivariant, deep neural net also permutation equivariant. So, and also from the previous lemma, the parameters in permutation equivariant deep neural net can be regarded as a subspace of the free parameters of free connected deep neural nets. So we can adapt the most of learning method to these parameters. So, and the number of parameter is compressed. So, and in the previous set anomaly detection tasks, there is an experiment. So the test accuracy is improved from 6.3 to 75. This is an experiment in deep sets. So the next one is permutation invariant neural nets. So today we need a theorem of representation. So a continuous function is permutation invariant if and only if f can be written of this form. So at first, there is a function of one variable phi, and taking sum, and then again apply a continuous function. So this decomposition, with this decomposition, we can see there is a what should I say, deep neural net approximating this function. So at first we map x1 by phi and x2 by phi and so on, and taking sum of all output and then apply law. This is a function f. So here we remark that for each phi, we can take the same MLP to approximate this. So permutation invariant neural net is defined like this. So each L is equivariant layers, and M is MLP, and sigma is orbit sum. So again, we can use learning method to this situation. Okay, then I will talk about some theoretical result and experimental result. So first one is, we deal with permutation, set of permutation, but Malone generalized the situation to arbitrary finite groups in SM. And instead of usual deep neural net, they use equivariant tensor networks for LI. And with this, so we can treat graphs or set of point clouds and set of graphs and so on. So, and also essentially he used so-called Hilbert finiteness theorem for showing universal approximation. Okay, and so we construct the some models, but the question is, so this model, it is enough to approximate permutation equivalent function or permutation invariant function. So this is called universality. So permutation equivalent deep neural nets and permutation invariant deep neural nets are known to be universal approximators for continuous permutation equivalent function and permutation invariant functions, respectively. So you can see the picture below. So the orange one is the set of continuous functions, and the green one is permutation equivalent functions. Permutation equivalent deep neural nets are included in permutation invariant function, but this is dense in this space. So any permutation invariant equivalent function can be approximated by permutation equivalent deep neural nets. So this is done by Laban-Baksh, and for the invariant case, it's proved by Maron. And I also did some contribution to this universality property. Okay, and also I will remark that for finite groups G, so same result is known. Okay, then another one is, this is joint work with Imaizumi-san and Kano-san. So we know for normal deep neural net, we know generalization bound. The generalization gap is bounded by something close to this. But the difference of G invariant case is the second term is divided by the order of the group. So this is a big difference, and the second term is, of course, leading term. So if in the case of point cloud task, the order of group is more than 1,000 factorial, very big value. And even in the case of set anomaly detection, the order of group is 16 factorial. This is also big. And the result is, it is a little bit hard to explain in one slide. So conditional neural processes, application to conditional neural processes. So CNP is a meta-learning method with permutation invariance in the data set. So if you want to do meta-learning, so each sample are algorithm. So, and the algorithm is the map which sends data to, for example, weights or model. So here, since the data is permutation invariant, so we have a permutation invariant structure. And also, so there are many results about this, Garnero and Gordon and so on. And with Kawan-san, so we did permutation invariant and group equivalent neural process. Okay. And this is so separating invariants. So it has been proposed that so the number of linear regions of deep neural net is an invariant that separates the expressive power of deep neural net and shallow neural net when we fix the number of parameters, for example. But the number of linear region cannot separate invariant neural nets and deep neural nets. So, and with Takai-san and Mashu-san, we defined a new invariant derived from the number of essential linear regions and the functions on it, and use it to separate invariant models and non-invariant models. So instead of definition, there is examples below. So the first one is, so you can easily see that number of linear region is 4, but this is a copy of a function of first region. So number of our definition is 1. And the next one is, so each linear region is congruent, but the function is different. Function takes different value. So the number of our definition is 2. Okay. So this is the conclusion. So we have reviewed the structure of symmetric deep neural net by Zahir et al. Deep sets. And this model has been generalized to finite groups by Malone. And there are various derived studies, including application to graphs and meta-learning. So, and also theoretical analysis is in progress. And such model will be important also in the future, I believe. Okay, this is the reference. Okay, thank you for your attention.
Yeah, thank you very much for your talk. So I think that is all for now for the AIP Open Seminar today for the Mathematical Science team. So thank you everyone for attending, and yeah, please have a nice day. So thank you very much.